Physics, here are the topics covered. Um, this section is going to be a lot shorter than everything else because physics is very math heavy, and there's nothing I can teach you in this session regarding maths that will be able to help you further because it's something that you just have to do lots and lots of past papers with. So if you're struggling with math, just do a bunch of math papers and past papers on physics maths. I'm going to teach you more on the theory side of physics, so it's probably going to be a lot shorter session compared to everything else. Okay, first let's talk about energy conversions. Energy stores in systems. So a system essentially is an object or a group of objects, things like a kettle filled with water. That's a system. So an energy is stored in these set systems. So they can do different forms like kinetic, thermal, electric. You need to know these types of electric stores, like what kind of things they are. So kinetic will be just like things like a car running, thermal, temperature, and all of that. You need to know what all of these are. I'm not going to explain them one by one. The understanding of energy, and you need to know this clearly, is that the conservation and dissipation of energy, and the principle of this is that energy is never created or destroyed. You never say it's created or destroyed. That's a very big mistake. Energy, however, can be transferred. So if we look at the explanation down here in the car diagram, we see that there is initial just chemical energy. The total is 4 bars. After maybe driving it for a while, some of it's going to turn to kinetic and some of it's going to become thermal. The total energy is still going to be 4 bars, but it's going to be transferred to different stores. Some of it's useful, some of it might be wasted. So in this case, thermal is probably going to be wasted energy because the thermal was probably from like the engine or the friction from driving the car. Some of it may just be wasted energy, but at the end of the day, all of it's just transferred, never created or destroyed. That's something important to note. These questions, all of this was math. So if you want to have a go at those, please do have a go after the session, but this is all math. Okay. With specific heat capacity, there are a few things you need to talk about with this. You have the diagram on the right, and it's showing you there is a change from like solid to liquid to gas. You can see that over time, and the temperature, when it's going just solid, all the way from the beginning from solid to liquid, there's a point where it just levels off. Time goes by, and internal energy is changing, but temperature is not. So you can see that when the place it is leveling off, that is the melting point or boiling point of change in state. So if something goes from solid to liquid, and you can see that there is a point of leveling off, that is the melting point. However, this is not to be confused with the internal energy. Temperature may not be changing, but the internal energy is still increasing. So this is something to remember. You have the specific heat capacity equation. Sometimes they will ask you to do math on this, which is energy equals mass times specific heat capacity times temperature change. You will be given this in the summary sheet, I believe. And that is just the specific heat capacity is just the change in thermal energy associated with the temperature change in a system. Latent heat of evaporation is just the energy required to change the state of 1 kilogram of substance without changing its temperature. So you can see in the area where it is the melting point or the boiling point, I told you internal energy is increasing, but temperature isn't. So that area is essentially the latent heat of either fusion or vaporization, depending on which one we're talking about. This is also given in an equation, E equals ml. I'm not going to explain those equations any further than that. Right. So let me just say this a bit more detail. Specific latent heat there's 2 different types: latent heat of fusion, latent heat of vaporization. Latent heat of fusion is the one melting point, and then latent heat of vaporization is the boiling point one. So those are the 2 ones, but they're all essentially just the energy required to change from solid to liquid. That's the understanding of specific latent heat, specific latent heat. There are a few questions on this. These 2 questions I don't want to go through because those 2 are quite simple. This question on the left, math. As again, this is more about just doing as much as you can. And you have the equation sheet, so it shouldn't be too difficult. Be careful with units. Physics especially, they love tricking you with units. So just make sure you're reading the units right and make sure you always write the unit. Even if they tell you you don't have to give it, you always write the unit. So the one thing I kind of want to look at will be question 8.4, which is saying that some thermal energy was transferred to surroundings when the water is heated. And it's talking about explaining the student values and all of that. So this is another applied question physics love to ask. They love to ask experiment applied questions. So again, this is all just doing a bunch of practice. So make sure with any of the math questions, just do it. Keep doing and doing them and doing them. But I just explained the theory part just in case they do ask you any questions regarding this, but it also helps you understand the math a bit better. Okay, electricity. This one is so heavily math-based, extremely heavily math-based. Likely in your exam paper, you're going to get 1 or 2 pages of just current or electricity, current, voltage, resistance. You need to be able to draw all of the diagrams. You need to be able to understand the series and parallel and all of that. But realistically, they're going to ask you like 5 math questions on electricity. So when you are studying for electricity, just remember the very basic concepts of it, but just know how to apply the equations. That's my main advice for this topic. So remember that protons, they have they have a positive charge, whereas electrons have a negative charge, and these opposite charges will attract, and the like charges will repel. So you can see from the diagram on the top, that one is showing you how the electrons are kind of flowing, and this is how electric current is kind of flowing through. The equation for this specifically is just current times time equals electric charge. That's the equation you need to understand. With resistance and potential difference, or some people would like to call it voltage, you can see that resistance is the measure of how difficult it is to form a particular voltage. And voltage itself is just a measure of electrical work done to move these carriers, to move these charges through the circuit. That's the work done to move all of these electric charges, these like little electrons and protons. Resistance is how difficult it is to form that, having a particular potential difference. You will get the equation V equals IR, again, given in the actual exam, so I'm not going to expand this any further. Electrical power and electrical energy transfers. If you guys want to know a bit more of understanding this, read through, I guess, some of it, but mainly, honestly, this whole slide is telling you P equals VI, which is another equation. And if you can put the earlier equation where V equals IR, you can put it into this equation to form P equals I squared R. Another equation. Electrical energy transfers, one thing I guess you do need to know is that battery and cells, they do work to move these electrons around. And because they're doing so much work, this transfers these chemical energy into heat energy sometimes, which can make the resistor very hot. So sometimes they might ask you, oh, why is the resistor hot after turning on the circuit for a while? It's because this chemical energy is transferred to electrical energy, and then that electrical energy can be transferred into thermal energy. And that's a waste energy. But essentially, that's the theory of it. It turns into thermal energy, causing it to be hot. It can be hot to touch. The other equation you have here is E equals QV, which is charge times potential difference equals energy. And this other one is energy transfer equals power times time, E equals PT. Those are the things about electricity, all fully math. This is also all math as well, so don't be too stressed about this. There is one thing I do want to mention, which is linking things with in parallel and in series. So this question kind of goes through that a little bit. So when you're linking stuff in parallel, so here it says, explain why adding resistors in parallel decreases the total resistance. So what you need to understand with movement of electrical currents is that it's always finding the way with the least resistance. Obviously, for example, if you're walking on a path and you see a busy road compared to a quiet road, you're going to prefer to go to the quiet road. That's somewhat similar to how current works. It's always going to find the area with the least resistance, with less obstruction in their path. So if you are putting resistors in parallel, adding resistors in parallel, it's going to decrease the total resistance because current has multiple different paths to go through. It's not all going through one single one. So adding them in parallel is just going to decrease the resistance. Whereas if you put them in series, current only has one pathway to go to. If it only has one pathway to go to, electrons can only throw through one pathway, and therefore it's going to have a lot of resistance, hard to go through. Putting them in parallel is just going to decrease it because it has multiple paths. I hope that is a good way of explaining it. That is kind of the only theory that is within electricity in physics. Besides that, all of it is just calculations. Now, this is where it's fully theory, so I will have to explain like in detail all of this with radiation. If you have any questions within radiation, please ask, because this topic is a really, really big one. They ask this in every single exam, and they have really good theory questions that can be very difficult. Okay, radiation. What radiation essentially is when there's a nuclei that undergoes radioactive decay, it's going to emit radiation and to become more stable. Radiation usually can ionize atoms. So this means that if there's radiation somewhere and there's like these atoms floating around, these can call these atoms to become ions. Activity is what you would call the rate of radioactive decay, and they're measured in emissions per second, or becquerels. I don't know how to pronounce that very well, but that is the unit. Remember the units very well. There are three main radiations I want to talk about, which is alpha, beta, and gamma. There is neutron, which is mentioned in some exam boards, but generally is not one of the biggest ones I want to mention. Neutron is is not too important, I would say. To detect this different types of radiation, this is not said on the slides, but to detect different types of radiation, there is these detectors called Geiger-Müller tubes, which help measure the radioactivity by counting the number of particles entering it. Hopefully you guys can see the chat, but I'm gonna type the name of this device out, because that is Geiger-Müller tube. That is what you would use to detect the radioactivity, and this counts the number of particles basically entering it. So with the alpha, beta, and gamma, we'll just talk about that. Alpha particles, you can treat them as a helium atom. So 2 protons and 2 neutrons. They're basically the same structure. You can literally treat it as a helium. They have an atomic number of 2 and a mass number of 4. 2 protons, 2 neutrons. Beta particles, you can treat as a high-speed electron, an E minus. So you would usually see a mass number of 0 and an atomic number of -1. It's technically not -1, but it's okay, yeah, you can't see the chat. There's something up with that. Okay, we'll type it out really quickly. There we go. Okay. Gamma rays, they are electromagnetic radiation emitted from the nucleus. And the neutron, as mentioned earlier, it is released from the nucleus as well. A neutron will essentially turn into a proton to release an electron. This is a bit wordy. I'm going to say that again. A neutron, so that's also considered a radiation, essentially. I will turn into a proton to release an electron. That's the best way I can explain it. Okay, but it's not too important. Don't worry too much about neutron. I want you guys to focus more on alpha, beta, and gamma. So with alpha, beta, and gamma, let's look at the thing on the side in the corner, the diagram on the corner. The different radiations have different penetrating rates, and they have different ionizing power. Alpha, its range is very, very low. It cannot go past skin. It can't go past a piece of paper. It's not very penetrating. It's the least penetrating. Beta is slightly better. It can go through a few sheets of paper, a few sheets of aluminum foil, but it cannot go through lead. It's a bit stronger when it comes to penetrating than compared to alpha, but it's still not too strong. The strongest one would be gamma. Gamma is so extremely penetrating. It can penetrate thick sheets of lead and blocks of it. The one, not lead, aluminum. It can go through and penetrate lots of aluminum and lots of paper. However, because there are things that emit such strong gamma radiation, you would want to store it in these lead boxes. This is where really strong gamma radiation, radioactive material is put, because it can't really go through lead. So again, alpha, least penetrating, beta, middle, gamma, most penetrating. Okay. Could you talk about motors and electromagnetism? Yes, I will try and do that. Okay. With ionizing power, so I said radioactive material can ionize atoms, so they can form ions from these atoms. So alpha is the exact opposite of their penetrating. Alpha is so extremely ionizing. So alpha can turn atoms into ions very, very, very easily. And that's very dangerous. Beta, again, is just the middle, and gamma is the least. It does not ionize very well. It's not very ionizing. So why am I mentioning all of this? It's because there are two terms that you need to know about. I need to type this out. Irradiation, which is the first one, and contamination. Okay. Irradiation, contamination. Irradiation is when you were exposed to radiation. So it's not inside you, you're not ingested it, but you've exposed yourself to radioactive material. This is where gamma radiation is very, very scary because alpha radiation is not going to go through your skin. You're safe. Beta, a bit more dangerous. Gamma can go through some of your tissues because it's so penetrating. Therefore, that is when it's the most dangerous. Contamination is when you've taken in radiation. So when you've eaten something that has radioactive material on it, or you've accidentally drank something with radioactive material, that if it's in your body, it's extremely dangerous if you have alpha radiation. Because, as I said, alpha radiation is very, very ionizing. This can be so harmful to your body because it will ionize ionize the atoms in your body, breaking down your tissues. This is so bad for you. So it's good to know which is most penetrating and which is most ionizing because they sometimes ask questions on that. Okay. Within this topic, let me just quickly. We also talk about nuclear equations and half-lives. So with the nuclear equations, we have an example of going through this in a bit, but the nuclear equations, the nuclear equations, the alpha particles I said are treated as a helium atom. Geiger-Müller tube is what detects, it's a detection device detector that helps detect radioactive activity. Radioactivity. Sorry, don't know when I was. Bleh. Yeah, radioactive material. That's what a Geiger-Müller tube is. So, radioactive decay, they always give you these equations, try and figure this out. If it is an alpha particle, as I said, it's like helium. If it's a beta particle, it's like electrons, so you have a -1. And we will go through a question like that in a bit. Half-lives, very basic of half-lives you need to understand is that it's just the time it takes for half of the nuclei to decay in the radioisotopes. There is an equation of 1/2 to the power of n to figure out how much is left. This is again math. So if you want a bit more practice on the half-lives and mathematical equations, please do have a look at that. The theory with half-lives that you need to know is that it is determined by the isotope of a nucleus. So the shorter the half-life, the faster an isotope will decay. And this is really unstable. So a longer half-life will be more stable. So a short half-life, the faster the isotope will decay, the more unstable it is. The question I want to look at is the second question here. It tells you this is the nuclear equations. So you can see the atomic number here is 36. You just need to basically do the math. You see that this is 0. 0 plus 85 is 85. So you're just going to have 85 here. Let me just type that out because I don't think that's horrible. Anyway, the bottom one, it's -1 plus something gives you 36. So we know that 37 minus 1 is going to be 36. So that's kind of the number we'll go with. I'm hoping this math makes sense, but this is just being careful with the top and the bottom numbers and being able to deduce what's the mass number and the atomic number. Bottom question, we're running out of time, so I don't want to go through this too much, but this is a really good question. So if you guys want to have work on radiation, 7.3, do this question. It's a very, very good question to do. It's a very good practice. And I have a feeling they might do this again this year, asking a similar question. So have a look at 7.3 if you have time. Okay, resultant force and acceleration. There are constant force and there's contact force and non-contact forces. You need to know the different types. That's kind of the gist of it. I know there are a few questions out there, but Yeah, we will go through that in a bit. So, resultant forces is just a single force that has the same effect on an object. And usually if it's opposite, you're going to minus these forces. If it's the same direction, you're going to add these forces together. That's how you figure resultant forces. So you can see here, it's only separated with horizontal and vertical. Horizontally, we see that there's 500 on the right, 200 on the left. Resultant force, minus them together because they're opposites, giving you 300. Vertical, 800 on the top, 800 on the bottom, minus them gives you 0. 0 resultant force vertically. So horizontal resultant force left is 300. This one's pretty simple, shouldn't be too difficult with resultant forces. Distant time graphs, this is, I think, a bit more focused on triple sciences, but I think both combined also has to do a little bit of this, but more focused on triple. Distant time graphs, generally, if this is the same kind of throughout distant time graphs and velocity time graphs. Distance time graphs, the slope will essentially be the velocity because it's just distance over time. If it's a straight line, we will know that this is a constant velocity. If it's curved, it's accelerating because the velocity is increasing as you go up. To figure out the equation, it tells you acceleration is velocity over time. Velocity time graphs, very similar. Velocity over time, if it's straight, it's going to be constant acceleration. So be careful with this. Distant time graphs, slope is velocity, straight line is constant velocity. If it's velocity time graph, straight line is the slope is acceleration, and the slope is if it's straight line, it is a constant acceleration. The thing you probably usually need to be able to figure out is the velocity sometimes. So if you want to figure out the velocity in the distance time graph, if it's curved, draw a tangent. If it's straight line, you can just figure out the gradient. If it's a velocity time graph, if you're trying to figure out the acceleration, you're gonna just figure out the gradient by using change in y over change in x. Again, same thing. If you want to figure out the distance using a velocity time graph, there's a way to do it. And that's figuring out the area under the line or the curve. So if it's a straight line, it's a constant velocity, a constant acceleration. That's going to be really easy because it's just the area of a triangle. However, if it's something like a curve, like you see in that horrendous box in the bottom right, you do not need to figure out the area under the curve. That is extremely difficult maths that I struggle to do. So you don't need to figure that out. The thing you will figure out is just figuring out the number of squares within the graph, and you'll be able to figure it out. Just counting the squares. Don't need to figure out the actual area. It's just an estimation. That's all you need to know with resultant forces and acceleration. So now we're moving on finally to waves. Let's talk about that. Waves, there are two types of waves. Before I go on, actually, does anyone have any questions regarding that? I can talk about electromagnetism and X-rays in a bit, so don't worry about that too much. Yes. Which ones are X-rays made of? Gamma rays. X-rays are made a form of electromagnetic radiation, so it's gamma rays. I think that's it. Okay. Okay, cool. So, waves. There are two types of waves, transverse waves and longitudinal waves. Transverse waves, they are caused by vibrations that are perpendicular to the energy transfer. Perpendicular, that's an important part. If it is longitudinal, the vibrations caused by the longitudinal waves caused by the vibrations, they are parallel to the direction of the energy transfers. So please be careful when you're answering the questions when you're comparing the two. Transverse is perpendicular to the energy transfer, longitudinal, parallel. It's also quite easy to differentiate the two based on their structure, as you can see on the top right. The transverse wave just looks like what you would typically think what a wave looks like. A longitudinal wave, you're going to have compressions and rarefactions. So the rarefaction is going to be the ones that are more loosely separated. Compressions are going to be the one that's closer together. Examples of transverse waves would usually be light or water ripples. Examples of longitudinal waves would be sound. That is the most classic example. Properties of the waves, you can see here, there's wavelength, there's the peak and the trough, the amplitude. That graph already tells you kind of what you need to know. The main part I want to emphasize on here is knowing the units of this. So you need to know amplitude. And that's the height of the wave. You need to know the wavelength is the distance between two equivalent points, and you need to know the frequency is the number of waves produced per second, or the number of waves that pass a point in a second. A period, this is a math question that shows up a lot. A period is the time it takes to produce one wave. And because we know frequency is the number of waves in 1 second, you can use the equation period equals to 1 over frequency. Remember the units, period is in seconds and frequency is in hertz. Always, always in frequency in hertz. Frequency is always in hertz, not kilohertz. Period is always in seconds. Remember to note that down. Oh, okay. With all of that, this is a bit, I think some of this might be only in triple, but generally this is all covered in both. The wave speed, there's also math again, calculated by frequency times wavelength. It is in meters per second, nothing else. Be careful with the unit, as I've said. There are other ways you can figure out the wave speeds. You can use a water ripple experiment. You can also figure that out by looking at an oscilloscope. A really interesting one is that by figuring out the sound waves, you can actually see how long it takes an echo to go from one side of the building to back to you. That's a way to figure out wave speeds. Those are just a few examples you can look at. Transmission is something I do want to look at because it's a little bit more theory-based. So, transmission. Waves can travel from one medium to another. However, from going from, for example, air to water is not as simple as just the wave just goes through. Even though the frequency doesn't change, the wavelength will increase or decrease depending on which medium it goes to. And because we know the equation, wave speed equals frequency times wavelength, the wave speed is also going to increase or decrease depending on the wavelength. So if there's an increase in wavelength, because frequency doesn't change, wave speed's also going to increase. If the wavelength decreases, the wave speed's also going to decrease when you're traveling through a different medium. So for example, the wavelength and speed is going to decrease when they go to shallower water compared to deep water. Deep water going to shallower water is a different medium. Different medium, decrease in wavelength, therefore decrease in speed. Also something to point out, this is triple science. Sound waves is triple science. Sound waves will travel at different speed in different mediums. So this is something to point out. This is also only in triple. This is something to know. Triple sciences, they love to ask you about the different spectrums. You need to know, not the specific numbers. I don't think you need to know the numbers specifically on what each of them are, but you kind of need to know the region. So radio waves is going to be the smallest, like not smallest, but like the largest wavelength. How to explain this? That's not a good way to explain it. But it's going to start with radio waves, and then it's going to be microwaves, infrared, visible light, UV light, X-rays, gamma rays. So when I said X-rays are kind of like gamma rays, it's like it is technically partly gamma radiation, but gamma rays is like higher compared to X-rays. So that's something to note. It's gonna go increasing in frequency. Those are gonna have a higher frequency as you go up. So gamma rays have a really, really high frequency, but they have a very, very small wavelength. You need to know you need to know the orders, and you kind of need to know not the specific numbers too much, but you need to know kind of the positions. So this is like a good picture to show you the positions of that. Okay.